Thank you, Lena, for that introduction, and thank you guys all for coming this afternoon. Before I begin, I'd just like to acknowledge my co-PI, Kate Quigley, who's really sort of the genetic brains behind this whole project, and also our collaborators, Andrew Negri, Lena Bay, and Madeleine Van Oppen. So I'd like to start by providing a broad spatial and temporal context for the thermal environment on the GBR. So we know that since the year 1900, across the entire reef tract, sea surface temperatures have increased about 1 degree C. But it's important to note that the thermal environment on the GBR is very spatially heterogeneous. And so if we take a look at the rates of warming on the GBR over the last 150 years, these are data from the Hagie sea surface temperature records, you'll notice that rates of warming are much more rapid south of the reef and offshore. And in the far northern reef, the rates of warming are actually the slowest. Now, if we take a look at some of the more recent data that has higher spatial resolution, we can look at the annual range in sea surface temperature. And you'll notice that on the central reef and the southern reef, especially inshore, the range is much greater than it is offshore and in the far north. And maybe most importantly, we can take a look at the sea surface temperature maxima, which are critical for the bleaching levels of corals. And you'll see that in the far northern reef, the maxima are much higher than they are on the central and in particular the southern GBR. So if we take a look at a latitudinal cross-section from Lizard Island in the north to Heron Island in the south, and we look at the temperatures over the year at these sites, you'll notice that there's a 3 degree or more difference in monthly temperatures along this gradient. And so what this tells us is that across the vast reef tract, coral holobionts, that is the coral animals themselves, their endosymbiotic algae, and their microbial communities, can actually show acclimatization and local adaptation to their environments. But even within a single population on a single reef, on a particular location on the reef, there's quite a range in the thermal tolerances in that population. So we can conceptualize this as a normal distribution where we have a few individuals that have very low thermal tolerance, a few individuals on the other end of the spectrum that have very high thermal tolerance, and then a majority of individuals that fall somewhere in the middle. And I'd like to note that we don't actually know what the shape of this distribution looks like at this point. If we have a thermal stress event like we've had the last couple of years, what can happen is the susceptible genotypes may be removed from the population, and the genotypes that can withstand extreme stress events may become favored. And so what ends up happening is this directional selection event where we have more thermally tolerant individuals in the population. So the 2016 and 2017 mass bleaching events served as potential selection events on the GBR. And these events may have removed the most thermally sensitive individuals from the populations, particularly in the far north, where the degree heating weeks were worst. And so what we have really is this background layer where we have corals that are locally adapted to naturally warmer conditions in the far north. And then on top of that, we have these recent repeated selection events that potentially removed the most susceptible individuals from the population. And so that's provided us an opportunity to identify the most potentially thermally tolerant individuals from those populations, from the bleaching survivors. This is just to illustrate what one of those bleaching survivors looks like. Neil Kenton took this photo in the far north in 2017. So the process of selective breeding uses phenotypic or genetic markers to actively select brood stock that have desired traits. And so humans have actually been doing this for millennia. Wheat is a great example where we've taken the plants that have the highest output and the fastest growth rates, and we've bred those together to shift the entire population to produce plants that have higher output. And we've seen this time and time again with other plants and animals, including with rice, with cattle, with dogs, and many, many others. I think I lost that. There we go. And I'd like to note that over the last 10 years, there have been extensive developments in this space in the aquaculture field, and so we're starting to learn from them how they've used this and apply it to corals. So with respect to restoration on the GBR, the aim is obviously to harness the adaptive variation within the populations to selectively enhance thermal tolerance. But it's also important to note that we can use this process to enhance other traits as well. So we could enhance growth rates or skeletal density or disease resistance or any number of traits that we think may help these populations proliferate into the future. So what this might look like on the GBR is we have corals from the far north that may be more temperature tolerant. We have ones from the central or southern reef that may be less temperature tolerant. We can breed those together and create offspring that hopefully have more temperature tolerance, with the ultimate goal of increasing the resilience of populations on the reef. And of course, the reason we're doing this is because we are trying to prime these populations for a rapidly warming world. So by 2050, temperatures could be 0.5 degree to 2 degrees higher than they are now, and so we're trying to harness some of that adaptive potential in those far northern populations to bring them to the central and southern reef. So this brings me to the question, are these bleaching survivors actually good candidates for selective breeding? So first and foremost, we actually need to confirm that those bleaching survivors are actually indeed more thermally tolerant than corals from the central and southern reef. Next, can we identify molecular and microbial markers of thermal tolerance? And this can include differences in symbiodinium communities, in bacterial or other microbial communities, and then also in the gene expression patterns. And then finally, are the offspring of these bleaching survivors more thermally tolerant? So today I'm just going to be focusing on this first research question. So to address this, corals were collected from 2 sites, Tijou Reef, which is in the far northern GBR, and then Back Numbers Reef, which is located in the central reef. So Tijou is heavily impacted by the 2017 mass-bleaching event. There was high mortality at this site. And Back Numbers Reef was largely spared from the bleaching event, so very low mortality, not a lot of bleaching identified. And we chose to work with Acropora spathulata because this was one of the few species that was actually present and abundant at Tijou Reef that was also still reproductive. So I just wanted to provide some context for the temperature at each of these locations. So these are the monthly mean temperatures from 2003 to 2016 in a density plot. Of course, Tijou is in red, Back Numbers is in blue. And I just put this up here to illustrate that Tijou, the environment at Tijou is quite a bit warmer than it is at Back Numbers. And if we look at the maximum temperatures at each of those reef sites, Tijou achieved a 0.5 degree higher maximum temperature than Back Numbers did. So the corals from the far north were collected by the GBR legacy team in November or October of 2017. They're actually put on a charter plane and flown back to Ames. And then the corals from the central reef were collected by an Ames vessel and brought back by sea. So to test these corals' responses to thermal stress, we performed an experiment where we exposed the genotypes to 2 different temperatures, 27.5 degrees, which is considered ambient and non-stressful, and then 30.5 degrees, which is considered the hot treatment. And we chose this temperature because when we look at the maximum sea surface temperatures from 2016 to 2018, that 30.5 degrees is right at the upper 2.5% of that distribution. And then just to give you a little bit of information about the experimental design, we had 4 replicate tanks at each of those temperature treatments, and then 3 technical replicates for every genotype that was tested. So the experiment started off all the corals at 27.5 degrees, and for the hot treatment, we ramped the temperatures that they exposed by 0.5 degree C per day up to 30.5. And then we maintained the experimental temperatures for 10 days, at which point we terminated the experiment and we stopped then because we wanted to stop the experiment when survivorship reached 50% of any of the populations. So to evaluate their responses to these thermal stresses, we measured 3 physiological metrics. So the first was their bleaching response, and we did this with the Coral Watch Coral Health Chart. I'm sure many of you are familiar with this. We used the D scale, so D1 to D6, to evaluate the level of bleaching of the colonies. We took these images on the first day and the last day, and then 2 intermediate points during the experiment. We also evaluated photosynthetic efficiency, or how efficient the endosymbionts within the coral hosts were performing. And again, we took these measurements at the start and end of the experiment, and then 2 midpoints. And finally, we just measured daily survivorship of the genotypes. And as I mentioned earlier, terminated when one population reached 50% mortality. So I'm going to go through a few of the results from this experiment, but I'd like to stress that these are preliminary. We haven't finished analyzing all of the data yet, so just as a caveat. So we'll start by looking at the bleaching data. And again, that bleaching scale goes from 1 to 6, where 6 is a fully pigmented, healthy coral, 1 is a completely bleached coral. And we'll start with back numbers reef, that central reef. So from now on, those will be in blue, and Tijou will be in red. So at the ambient treatment, at the end of the experiment, the back numbers corals are sitting at a healthy 5.5 on that bleaching scale. But then when we compare that with the hot treatment, we see that there was a significant decline or significant paling of those corals throughout the duration of the exposure. Now when we compare that with Tijou, what you'll notice is that the corals from Tijou overall were just a bit paler than those from back numbers. But when we compare the hot treatment with the ambient treatment, you'll notice that there was no difference, and so those corals didn't pale at all throughout the experiment. And so really what we're interested in is the difference between the ambient and the hot treatment for each of the 2 populations. And so you see those differences plotted on the right of the screen. And you'll see that the central corals performed more poorly than those from Tijou. And sort of just to give you an idea of what this actually looks like, this is an example of one of those fragments from back numbers, that an image that was taken on day 1, the first day, and then the final day. We can compare that with Tijou. So overall, Tijou was a bit paler, but it stayed consistent throughout the experiment. Now we'll move on to photosynthetic yield. The results of the yield data really well corroborate the results of the bleaching data. So we saw that there was a decline in the yield for the back numbers corals from ambient to hot. But when we compare that with how the Tijou corals performed, a little bit lower overall, but no change from ambient to hot. And again, we can look at those changes graphically and see that there's quite a big difference between those 2 populations. And then finally, survivorship. So at back numbers reef, all of the corals that were treated in the ambient condition performed very well. The survivorship was near 100%, but survivorship dropped to about 70% when they were exposed to that temperature treatment. Now when we compare that with Tijou, what you'll notice is right off the bat at the ambient temperature, Tijou didn't perform as well. If we compare that with the hot treatment, there really wasn't a change, a statistical change, because that variance is so high, but there still was a bit of a decline in the means. And again, you can see that illustrated in the plot on the right. And so what this shows us is that overall survivorship for the Tijou corals was lower than those from back numbers. And what we think might be happening here is that there may be some kind of latent effect from the thermal stress that we're detecting even at the non-stressful treatment temperature. So these corals have gone through, they've run the gauntlet 2 years in a row with back-to-back bleaching, and then we transported them by plane back to Ames, and then they spawned, and then we performed this experiment. And so it could just be all of these effects sort of compounding on one another to lower their health, their overall health. But that said, there were still some promising genotypes that performed pretty well in these experiments. So that leads me back to my first question that I posed at the start, which is, are bleaching survivors good candidates for selective breeding? And at this point, I think the answer is we aren't quite sure yet. We don't know. We're still in the very early stages of testing these northern populations. And we're waiting on some genetic data from this experiment and waiting to analyze the selective breeding data from this experiment. But we also have others in the works to look at some other northern populations. And I think that's really important because if you remember back to that temperature plot that I showed you at the beginning, Tijou is warmer than back numbers, but it wasn't extremely warm. And so I think if we can go up to the far north and maybe go inshore to some of the sites that really heat up at least 1.5 to 2 degrees above what we see in the central,